Hello, and welcome to another episode of Talking with the Experts, the video podcast where we chat with thought leaders about today's growing natural hazard risks. Risks like wildfires, floods, severe storms, and lightning. I'm Mike Nichols, your host and AM's content and social media manager, and today we're looking at cutting-edge research in the field of lightning science. To help me, I've got three up-and-coming researchers in the field to share some of their latest research. The first two guests come to us from AEM's research and development team. First up, we've got Dr. Jacqelyn Ringhausen. Hey, Jackie, thank you for being here. Really do appreciate it. My understanding is you've got some weather jokes. Any chance you can share one of those with us?
I have a wind turbine joke.
Yeah, sure.
So, what is a wind turbine's favorite music genre?
Favorite music genre? No idea.
They're big heavy metal fans.
Oh. That's great. Well, anyway, whether or not she's got the best sense of humor, Dr. Ringhausen is an excellent lightning scientist. She joined AEM last year as a postdoctoral lightning researcher since receiving her PhD in lightning physics from the University of Alabama in Huntsville back in 2021. She's built a really impressive resume as a field researcher. She's interned for both the National Weather Service and NASA. She's helped deploy a variety of environmental sensors into the field, designed and built lightning sensors, and tested their detection efficiency. She's even helped run a field deployment for to collect 3D lightning data inside Hurricane Ian. And today she's going to be discussing some of her recent research into the ways wind farms influence lightning activity, thus the wind farm joke. And next up, we've got Dr. Yanan Zhu. Hi, Yanan.
Hi.
How are you doing, sir?
Me. Good. How are you?
Good. Really appreciate being here. Dr. Zhu, he joined AEM's research and development team as a lightning scientist back in 2022. And prior to joining at AEM, he received his PhD in lightning science in 2017, followed by postdoctoral research at the University of Alabama in Huntsville, where he contributed to the development of a low-frequency lightning mapping network. His current research interests include lightning physics, instrumentation, the application of machine learning techniques to geoscience, and lightning-initiated wildfires. And in his latest research, he's looking at lightning and wildfires and their interaction. So that's what you'll be sharing with us today. Is that right?
Yep.
Excellent. And then last but not least, we've got an extra special guest from the New Mexico Institute of Mining and Technology. It's Dr. Adonis Leal. Welcome, Adonis.
Hello.
How are you doing?
Thank you. I'm doing well, and thank you.
Dr. Leal is he's currently an assistant professor in the Department of Physics at the Langmuir Research and a Langmuir researcher at New Mexico Tech, which is home of the famed Langmuir Laboratory for Atmospheric Research. Dr. Leal received his PhD in electrical engineering from the Federal University of Para in Brazil back in 2018, where he would go on to become an assistant professor and head of the university's Lightning Research Laboratory. Dr. Leal's current research interests include lightning protection for renewable energy systems, lightning fires. By the way, Yana, that means Dr. Leal might have something to say about your research.
Yep.
And then remote sensing and lightning signal processing, including data mining and artificial intelligence. And it's that last area of research that he'll be talking about today. And with that, I think we can go ahead and dive into our conversation. Are you guys up for it?
Yeah.
Sure.
Yes.
So, Adonis, since you're our outside guest, why don't we go ahead and start with you? Let's have you share maybe the Cliff's Note version of your latest research on using AI to distinguish between in-cloud lightning and lightning that makes it to the ground.
Yeah, sure. So maybe I would like to start with a short story about this research project, about like this idea. So during my PhD back in the Amazon region, I developed a low-cost system to record lightning electric field waveforms. And at some point, I figured out that for 1 day of data, I had like 50,000 waveforms to look for a single day. So that's like impossible to analyze all the 50,000 by eyes. So that's why not try to teach a machine to classify those waveforms for me? So that was like the beginning of the project. And After that, I came to the US. I met the AEM people, and they had a huge data set, much, much bigger than my 50,000 waveforms, right? Because they have sensors all around the world, and all the sensors collect the electric field waveforms. So that was like the biggest challenge. Organize the data set and try to teach the machine, the computers, the algorithms to recognize the different types of lightning. And after the years, I could like understand better how the machine algorithms work. And then we worked together for the past 2 years to develop this like very new, brand new algorithm to classify between cloud to ground and intercloud lightning pulses. And also, the polarity of the pulses. And I would say that nowadays, the Earth network's total lightning, the accuracy for the classification is higher than 95% for the network as a whole, like in the globe. So I
Wow.
believe that's the short answer.
That is really interesting. Just for those of us who may not be as familiar with lightning classification, maybe you could just back up and just say something about why is it that we distinguish between cloud to ground and in-cloud lightning in the first place?
Yeah, sure. In nature, we have these main two types of lightning flashes. The ones that remains in the cloud, which we call intercloud flashes, and the ones that goes all the way to the ground and make the connection between the cloud and the ground, we call cloud to ground lightning flashes. And as you can see, the ones that touch the ground, the cloud to ground, they are like more dangerous to human people, to the electric systems, to telecommunication systems, because essentially all like the human systems, they are based on ground level. So that's why they are like more dangerous to people. And that's why we must care about them. But on the other hand, the intercloud lightning flashes, they are also important because, for example, imagine that you are in an airplane. Intercloud lightning can hit your plane. So you must be aware about the locations of the intercloud flashes. And also, like different research have shown that intercloud flashes, they are, for example, related to severe weather, like the initiation of severe weather. So that's another thing about intercloud flashes. And if you misclassify them, you can do like a wrong warning. For example, if you have people working on the ground and you misclassify a cloud to ground as an intracloud, those people that have a warning system on the ground, they would be in dangers because you misclassify your lightning, right? So that's why it's very important to have a very accurate classification, because we do need different type of like warning systems for people that are on the ground, for systems that are on the ground, and for systems that work with information about intercloud flashes, I would say.
That's great. Jan and Jackie, how do you react to that? What are any thoughts on what he's been saying?
Yeah.
Yeah, I think especially for a lot of for use cases in like airport, they do rely on the accurate classification of cloud to ground lightning a lot, as I know. Yeah.
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 I would say, my biggest takeaway of why it's important to classify them is more on the scientific, like he mentioned, storm strengthening and seeing a lot more intercloud lightning. So intercloud lightning is a lot more common than cloud to ground. Like it's a much larger ratio of it happening versus coming to ground. And a lot of studies have shown that, when you have an updraft strengthening, it causes a lot more turbulence. And when you get turbulence, you get all these little pockets of charge. And that's why you're getting a bunch of little intercloud lightning happening. And it's signaling, hey, your storm's strengthening. And sometimes they try to do things like a lightning jump where you can put out a warning ahead of time that the storm could potentially become severe. So
Yes.
That makes sense.
I have actually a question. Might be interesting. That is, we're talking about classifying, differentiate the cloud to ground and intra-cloud lightning based on their waveforms. And in general, can you let us know, Adonis, how do they, how do you tell, like, how different those pulses are, like intra-cloud and cloud to ground?
Thank you for your question, Yanan. So, well, before like the machine learning algorithm and so on, all the networks classify the different types of lightning based, for example, in the pulse width. So usually cloud to ground lightning, cloud to ground pulses, they have a wider pulse width. And another thing is, for example, when you are far away from the lightning channel and you record the electric field signature with your sensor, when you are too far away, you can see the ionosphere reflections. So a lightning is going to emit electromagnetic signals that's going to propagate in all directions. And one of those directions, it is the ionosphere. And the ionosphere is going to act as like a mirror that's going to reflect your signal and going to arrive at your sensor. And we can see those signatures in our like waveforms. And the main difference between those reflections from cloud to ground and intercloud is because the intercloud is going to show two reflections, one that comes from the ionosphere and another reflection that comes from ground, because you are an elevated source. But
I have a
the
question.
cloud to okay,
Just for people listening,
yes,
can you
go
explain
ahead.
the ionosphere a little bit? Like, what is that for listeners out there?
Yeah, sure. Thanks for your question. Yeah, the
Yeah.
ionosphere, it's like a layer in the atmosphere that's full of electrons. Like the electrons density is very high. And because the ionosphere is very conductive, it can reflect electric signals. So you can like imagine that the ionosphere is kind of a mirror, and the electromagnetic signal it's a laser or a light beam that's gonna touch the ionosphere and reflect to your sensor. You can imagine something like that, right? And yeah, so the main difference between these two pulses would be the ionosphere reflections and the pulse width, and sometimes the raise time. So those are the main features that we as human beings that we can observe. But the machine learning algorithms, they can find the different features that our eyes cannot catch. So that's why it's like a very good idea teach the machine learning algorithms to classify for us, because we can teach a few features that we are able to recognize, but the machine learning algorithms, they can recognize much more features that our eyes cannot catch.
Yep, I agree. It's a pretty good task for machine to do.
Yes.
So,
Yeah.
Yanan, if we turn this around on you, I would imagine that distinction between cloud to ground and cloud lightning, that's pretty important in the line of research you're doing on wildfires and lightning.
Of course, yeah. We do rely on the accurate classification because only cloud to ground lightning can ignite wildfires.
Yeah, makes sense. And while we're here, why don't we just go ahead and have you give us the quick high-level overview of what the focus of your research really is.
Sure. So my research focused on the understanding how lightning interact with the environment to ignite wildfires. So we know that lightning is responsible for some of the largest and most destructive wildfires, but predicting when they will start or where they will start is very challenging. And my work combined the lightning detection network data, our Earth network data, and the environmental data, condition data, things like precipitation, fuel moisture, temperature. So we combine those data to better understand what makes lightning strikes start a fire, while others do not. At first, I analyzed how rainfall or precipitation and lightning activity are linked. And then I expanded my analysis to including more environmental factors like humidity, fuel conditions, to get a full picture of what conditions could lead to fire ignition.
That's interesting. So how do they line up? I mean, or not line up, right?
Yeah. So a lot of my analysis results so far show that precipitation is the most important factor, probably followed by fuel moisture. Fuel moisture is the moisture content in the dead fallen leaves or branches on the floor usually. And interestingly, actually lightning parameters, like how strong lightning is not as important as we thought based on my research so far.
That's interesting. That is really interesting. Jackie, Adonis, what do you guys think of that? Love to get your reactions.
Yeah.
So go ahead, Jackie.
Okay. So you're saying the moisture is most important. So does that mean if you are in a place that's very moist most of the time and it's getting struck by lightning all the time, there's just never going to be wildfire? Or is there like a threshold where, okay, once there's this much lightning happening all the time, you're more likely to get lightning? Like, what's the threshold of it needs to be dry versus wet to get a ignition from lightning?
Yeah, probably. I would say there's a threshold in precipitation when if a lightning can start a fire. For example, I look at precipitation at the different time scales, specifically at 24-hour scale. If you have 40 millimeter precipitation daily, you're basically impossible, I would say, based on my data, impossible to get a fire. Yeah, but it definitely depends on other factors as well, like the humidity at the ground level, the fuel condition at ground level. So, yeah, that's. But I would say again, precipitation is probably the most important factor so far.
So, which region gets the most lightning-caused wildfires? Like in the United States?
In U.S., as you know, probably a lot of people know that California is definitely the state that got a lot of fires. But for regions, you get most of our fires in Southwest region, including California, and followed by Northwest, like Idaho, Oregon, Washington State. But in general, as you expected, the West Coast has a drier climate compared to the East Coast. So West has probably 4 or 5 times more wildfires than the East Coast.
Even though they have less lightning. Interesting.
Yeah.
Although wildfires are becoming an increasing problem in the East, right?
Yes.
Yeah. Do you have any information about like how the vegetation is gonna affect the initiation of the fires?
Yeah, it's a good question. I actually do including a little bit of data in the vegetation. Well, what kind of, based on the satellite data, remote sensing of satellite, tells you what kind of this region, what kind of what is the vegetation in this region, like a resolution of about 500 meters or so. But I do not go really deep on that, so I do not have a clear answer for you. But based on the literature I've been reading, there's certain type of trees. I don't have the name off the top of my head, but certain types of trees have a higher probability getting lightning fires than others. So I think definitely this is the one thing that's worth looking at in the future.
Makes sense. Hey, Jackie, I'd love to get your reaction to some of what Yanan's been saying and some of what Adonis has been saying. I mean, I would imagine energy companies in general, whether they're wind generated or not, they might have a vested interest in knowing A, where lightning's reaching the ground, and B, where there might be elevated wildfire risk.
Yeah, for sure. I mean, that makes sense. You want to know where wildfires are going to start, because if your instrumentation's in the path of that fire, that's important to know. And B, your instruments themselves getting struck by lightning is important to know. Like, how often is it climatologically likely to happen when you're building these sensors, and having the correct protection on your sensors. And the best way to protect them is another avenue that a lot of people are researching with lightning, especially with wind turbines.
And speaking of that direction of research, why don't we go ahead and turn to what you've been looking at in terms of that interplay between lightning activity and wind farms.
Yeah, so I've been researching wind turbines. I did a project in New York looking at winter lightning and wind turbines. There was a wind farm right up there, and we were looking at how the lake affects snow and how often the turbines are getting struck. And then when I started here at AEM, we met with Alan Hall and he was asking us to look into a case study related in Oklahoma. And from that part,
I'm sorry to interrupt. Alan Hall is
yeah. Yeah. Alan Hall is weather guard. He asked us to look into some lightning patterns around some turbines in Oklahoma. And from there, I was like, why not do a whole climatological study on this? And really started digging into, okay, what is the climatological likelihood of lightning and how are the turbines changing the patterns of lightning? And also, are they having any effect on the storms themselves? So doing more case studies of the storms moving past the turbines and what's happening to them.
That's interesting. I did have a chance to look at some of your research.
Okay.
Yeah, and you mentioned that the data from our in-house Earth Network's Total Lightning Network, that showed a clear increase in lightning pulses over an area after turbines were built. But then you had another data source, the geostationary lightning map, that did not show a clear signal. Is that right?
That is correct. So
I would love to know your thoughts on what might account for that difference.
Yeah. So what you're referring to is I looked at a wind farm and looked at the lightning occurring over it before the turbines were built and after they were built to see if there was a clear change in the signal. And there was in the Earth Network's data, but not in GLM. And the geostationary lightning mapper is this lightning sensor that's detecting from space. So it's looking for light escaping the cloud top, basically. It's in a very narrow band. And if you think about it, if we have this upward lightning coming from a wind turbine, you're going to be at the bottom of your cloud. And if you're at the bottom of your cloud, in order for that light to escape the top, it's going to go through a lot of scattering and some absorption as well. So it's going to be a lot harder for light to reach the top. And the amount that does might be smaller than the GLM can detect for its thresholding. So that could be one reason why it's not seeing it as well. You've got these small pulses or lightning strikes coming from turbines. They're usually not the most energetic compared to like your big cloud to ground flashes that you see typically. And they're not as energetic, they're not as luminous, and they're also having to travel through a lot of the cloud. So it's going to make it harder for GLM to see.
So if that hypothesis holds water, I mean, to really study the phenomena, you need a ground-based network, right?
Yeah. You would want a ground-based. I mean, the best thing for when you're looking at these ground-based sensors, you would want an LMA potentially, because they can kind of map it.
An LMA is, I'm sorry?
Sorry, a lightning mapping array. So they're detecting in a very high frequency range, and they can see like these little sources and map it in 3D. The same thing with an interferometer. You can also map things in 3D. It looks similar. And also video, like having actual video of these lightning flashes is good. And eventually you can use these ground-based truths to train something like Adonis's model. He could potentially have a signal for upward lightning. It might have a clear signal that we could use in the future.
Oh, that's great. So Adonis, Yanan, let's open it up to you guys. I mean, I don't want to hog all the questions. So
yeah, my question is, what is special about this lightning from the turbine or striking the turbine compared to the normal cloud to ground lightning?
Yeah. I mean, it's usually not quite as strong as when you see your normal cloud to ground lightning, but basically it's being generated by this tall pointy object that you're putting in the path. So, this happens with towers too, but wind turbines, especially when they're moving, they're getting rid of that kind of space charge that sits there and it will kind of shield things. That's why tall objects aren't constantly getting struck. When it's moving, it can make it easier for it to get struck. And so a lot of times when you have this lightning that's attaching to these tall objects, it's not actually coming up all the time. There'll be a lightning event that's happening nearby and it will actually trigger these upward flashes from the turbine. And this is because it can't overcome that until these branching flashes, sorry, I'm saying this really weird, but it's hard for it to overcome it until it gets like a leader moving over it. And that makes the charge neutralized above. And so it's easier for it to move upward and then connect with the cloud. However, this is also seasonally dependent. So in the wintertime, it's a lot easier for these upward flashes to actually self-initiate because the tall objects are essentially in the cloud because winter storms have a lot lower cloud base. So it's a lot easier for it to trigger these upward flashes.
Well, that's interesting.
Yeah.
I see.
Mm-hmm. So that's why you'll see a lot more in the wintertime of the signal.
Okay.
Makes sense.
So perhaps in the same way, have you noticed any difference in the lightning types before the wind turbines, the wind farms installation, and after?
Yeah. I definitely have seen, specifically in the winter months, there's a lot more cloud to ground lightning right over these turbines, and it's a very clear signal. In the summertime, that signal is not as clear. And also the polarity of the flashes is very different. So there's a lot more negative lightning than after the turbines are built versus before. And this is not just CG lightning, this is also intercloud lightning. There's more negative intercloud and cloud to ground lightning happening over the turbine.
Any thoughts on why you would have more intercloud?
Yeah. The cloud to ground makes sense in my brain because you're having these usually it's a positive leader coming up, so you'll get this negative discharge. But that's an interesting one, and I'm not 100% certain. It's implying either that there is a difference in the charge structure inside the storm. You usually get negative ICs more in when you have an anomalous charge in the storm. But also it could be some classification issues just with upward leaders themselves, because they are a little bit tricky. They're not your typical signal that you'll see. So it could be they're misclassifying negative CG as a negative IC.
To follow up on this question, do you think it's possible for the wind farm or the presence of wind farm could possibly modify the characteristics of thunderstorms?
Yeah, that's one of the things I'm like really researching right now, like really digging into it. And the few cases I've looked at, there is some change, and it's not going to be consistent across all storms. It's going to be dependent on things like how did the storm move over the turbines and what orientation are the turbines laid out when the storm's moving across. It also depends on your cloud base height, what type of storm, like how big a storm is, because if it's too big, it's not going to have as much of an impact versus a smaller storm that's just starting up. But we are seeing that there is some sort of change in it. So the theory is that when you have these wind turbines, they're usually spinning. They turn off at around 55 miles per hour is typically when turbines shut off during storm. So when they're spinning, they're adding this turbulence to the boundary layer of your storm, and this can get ingested, and then it can either strengthen the storm if it's going with the winds, or it could potentially weaken the storm. So I'm actually working with a modeler, and we're trying to model that in the work, and we've parameterized the wind turbines, and we're seeing some differences, which is cool.
Yeah, cool.
Very nice.
Yeah.
And do you think like the size of the wind farms play an important role, like in the lightning configuration during the thunderstorms?
Yeah, I mean,
so
I would assume.
Yeah, so I'm thinking about that. So perhaps maybe in the future, when you design a new wind farms, you have to come up with a specific size or specific shape to try to mitigate the hazards from lightning.
Yeah, that's totally true. And wind turbines, like the newer wind turbines they build, are usually taller. So with time, they've been building them taller and taller, and that makes it a lot more likely to have an effect on these storms because it's reaching higher into the atmosphere. It's going higher into the boundary layer, and it's also more likely to get struck by lightning when it's taller.
Okay, thank you.
That is just fascinating research, and it sounds like a lot more research to be done. So,
I'm in the thick of it right now. It's exciting and it's fun.
All right. Well, I know we could go on for hours and hours talking to each other about what you guys are doing. It's fascinating research, and I love to hear about the overlaps, right? But I also want to be respectful of your time. So, Jackie, Yanan, and Adonis, thank you all for taking time out of your schedules to come on the program today. I really do appreciate it. I found thank you guys. I found the discussion to be both entertaining and eye-opening. And I hope all of you listening, I hope you did too. If you'd like to learn more about any of these topics, we have a new blog post coming up that'll be discussing Dr. Leal's research into using AI to improve lightning classification. And we have Dr. Ringhausen just recently discussed her research on lightning and wind farms on a recent AM webinar. If you're watching this on YouTube, we'll have links to both of those resources in the comments. Otherwise, you can also find them on our website at am.eco. So with that, until next time, this is Mike Nichols for AM and for Talking with the Experts.